the gaseous state. An understanding of just what gas pressure is and what it can do for us can make life a lot easier and safer. And we see some explosions here in these pictures. We're going to talk about just what exactly creates gas pressure. I like this picture. Do you recognize this railroad car? Atmospheric pressure is what crushed this. And I can't give you an example of a railroad car, but I can give you an example of this with an aluminum can. So check this out. Here's another example of air pressure. First, water is added to the aluminum can. The water in the can is then boiled. When steam comes out of the can, all the air in the can has been replaced with hot steam. You could not survive in the can if you were inside it, because not only is it very hot, but there is no air. It is all steam. The pressure of the steam in the can is the same as atmospheric pressure outside of the can. The pressures are balanced inside and outside the can. When the can is inverted and placed into the ice water, the steam inside the can condenses, turning into a very thin film of water along the insides of the can. There is very little gas left inside the can. In other words, a vacuum is created inside the can. Vacuums do not have pressure because they do not have gas. With no pressure inside the can, atmospheric pressure crushes the can from all directions with a weight of 14.7 pounds over every square inch of the can. Here it is again in slow motion. So what are some common units for pressure? Well, there's PSI, that's what we fill our tires up with, right? Pounds per square inch is PSI. Atmospheres, millimeters of mercury is another unit for pressure. In fact, 1 atmosphere is 760 millimeters of mercury. Volume, how about volume? What are some common units for volume? Well, volume is length times width times height, so any distance cubed is volume. Cubic centimeters, cubic meters, milliliters. In fact, 1 cubic centimeter is 1 milliliter. Pressure, and what happens when you make a gas colder? So here's a balloon, and we know that it's surrounded by atmospheric pressure. So the pressure inside the balloon is 1 atmosphere, and the pressure outside the balloon is 1 atmosphere. And we also know that 1 atmosphere is also about 14.7 pounds per square inch. So if I blow inside this balloon, I'm going to increase the pressure inside the balloon, and it's going to stretch it and make it big. Okay, let me tie it off so the pressure doesn't escape. Okay, so what caused this pressure? Well, the inner surface of the balloon is being stretched. It's being struck by the air molecules. So if I drew a square inch on here, what's the average force that's being exerted by these air molecules by striking that square inch on the inner surface of the balloon? That's the pressure inside the balloon. How could I reduce that pressure? Let's slow down those air molecules. Let's make them move slower. Then they'll strike this square inch with much less force. So I'll have less pounds per square inch of pressure. I could slow these air molecules down by putting this entire balloon in the refrigerator, and it would shrink a little bit because now the pressure has been reduced by slowing down those air molecules. But I want to really slow down these air molecules. In fact, I want to make this balloon so cold that it's negative 330 degrees Fahrenheit, a lot colder than any refrigerator can handle. How am I going to do it? I'm going to pour liquid nitrogen over this balloon. Now, if you make nitrogen to be around negative 330 degrees Fahrenheit, it will liquefy. So that's what this is. So as I pour the liquid nitrogen over the balloon, the air molecules slow down. And in fact, what's interesting, when I stop pouring the liquid nitrogen, the air molecules start warming up. They start traveling faster. So when the balloon gets back to room temperature, the air molecules are traveling at their original speed, room temperature speed, so the balloon gets back to its original volume. Pressure and temperature. So let's see if we can come up with an equation that's going to allow us to predict changes in pressure, temperature, or volume of a gas. Let's start with the ideal gas law. PV equals nRT. So P was pressure, V volume, N in the number of moles, R is a gas constant. R is 0.0821 liters atmospheres over moles Kelvin. And T is just temperature in Kelvin, though. Now, if we rearrange the ideal gas law, we'll have PV over nRT equals 1. Let's add some subscript. Instead of writing initial and final, let's use 1s and 2s. So I have a P1, a V1. I have all my initials. So since they equals 1, I could do this, write the same equation, but with 2 as a subscript. So there's my expression. Now we can simplify it a little bit here yet. So let's rewrite it. Okay, so the 1s are my initial, the 2s are my final. Now there's certain things in here that don't make sense to have in our equation. One is the R, because it's a constant. It'll just cancel out. So let's just erase it. Then the other one that we can cancel out is the N. The reason why we can cancel out the N's is because we're not going to change the number of moles. So they cancel out too. So here's our expression. P1 V1 over T1 equals P2 V2 over T2. And this always works, just that the temperature has to be in units of Kelvin, capital K. Standard temperature and pressure, we call it STP. It consists of a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. So know these conversions, know these simple relationships. If you ever want to get into Kelvin, just add 273 to Celsius and you'll get it. A liter is 1,000 milliliters, which is the same as 1,000 cubic centimeters because they're the same thing. A milliliter equals a cubic centimeter. And in an atmosphere, you have 760 millimeters of mercury, or 101.325 kilopascals, which equals 760 torr. These I'll give to you. Don't worry about knowing those. So let's try solving some problems. A sample of nitrogen gas at 18 degrees Celsius and 860 millimeters of mercury has a volume of 3.92 milliliters. What is the volume at 10 degrees Celsius and 0.36 atmospheres? Seems to me we have two equations to work with. One is PV equals nRT. The other one is that P1 V1 over T1 equals P2 V2 over T2. So which equation fits this problem? What I see is I see two temperatures. Heck, I even see two volumes. So this is definitely this type of problem. Okay, that's how I recognize these. So let's go ahead and see what we can plug in. P1, V1, T1, see what we can find. P2, V2, and T2. How all these problems work is they give us everything except one of these variables. What is the volume at 10 degrees Celsius? So they want to know what the volume is at 10 degrees Celsius, but that's equal to 283 Kelvin. I just add 272 to it. What is the P2? 0.36 atmospheres. I need to know what P1, V1, and T1 are. It looks like P1 is 860 millimeters of mercury. The temperature is 18 degrees Celsius. But add 273, 291 Kelvin. My V1 is 3.92 milliliters. So I should be able to plug and chug and figure this out. Now, your units need to be consistent. Notice how my pressure units are not consistent, so let's fix that first. Either we pick atmospheres or millimeters of mercury. It doesn't matter which one. I'm just going to go to atmospheres. There's 760 millimeters of mercury in 1 atmosphere. That way my millimeters of mercury units cancel. 860 divided by 760, 1.13. So now everything's in atmospheres. That'll work. So my P1 is 1.13 atmospheres. My V1 is 3.92 milliliters. T1 is 291 Kelvin. P2, 0.36 atmospheres. V2 is what I'm trying to find. And T2 is 283 Kelvin. So notice how all my units are going to cancel out here. Kelvins are cancel, atmospheres cancel. My V2 is going to be in milliliters. My V2 is going to be in milliliters. And remember the game plan here. It's go along the diagonal whenever you want to move something from one side to the other. So that 1.13 times 3.92, I'm going to move the 283 up there onto the top. The 291 stays on the bottom. Let's move the 0.36 down there with it. So that'll be my answer in milliliters. 1.13 times 3.92 times 283, divide by 291, divide by 0.36, I get about 12 milliliters. Liquid methanol can be produced by reacting carbon dioxide gas with hydrogen gas in the presence of a catalyst. Water vapor is the other product. How many volumes of hydrogen are required for each volume of carbon dioxide when each gas is at the same temperature and pressure? Sounds like a complicated question, but it's really not. Let's write out the reaction. Liquid methanol can be produced. So CH3OH with a little liquid sign. By reacting carbon dioxide, so carbon dioxide gas is a reactant, with hydrogen gas. That's also a reactant. In the presence of a catalyst. So I guess you could write catalyst over the arrow. Now I just need to balance it. I have 6 hydrogens. So put a 3 there. I have 2 oxygens. It's nice and balanced. Okay, see if we can answer this question. How many volumes of hydrogen are required for each volume of carbon dioxide? So when the gases are all at the same temperature and pressure, then they have the same number of moles. So you can be talking about volume or moles. It really doesn't matter. They're the same thing when you're at the same temperature and pressure. For each volume of carbon dioxide, you have 3 volumes of hydrogen. It's just like saying for every 1 mole of carbon dioxide, you have 3 moles of hydrogen. Well, when the gases are at the same temperature and pressure, volumes are the same thing as moles. So you have 3 volumes of hydrogen for every 1 volume of carbon dioxide. So the answer is 3. Pantothenic acid is vitamin B. Using the Dumas method, you find that a sample weighing 71.6 milligrams gives 3.84 milliliters of nitrogen gas at 23 degrees Celsius and 785 millimeters of mercury. What is the volume of nitrogen at STP? Remember STP, 1 atmosphere 0 degrees Celsius. So we're changing temperature, we're changing pressure. We're going to go back to our P1 V1 over T1 equals P2 V2 over T2. That type of problem. So let's just list them out. So let's say at 23 degrees Celsius, I have 785 millimeters of mercury and 3.84 milliliters of nitrogen. Then the other second set of conditions, what is the volume at 1 atmosphere and 0 degrees Celsius? So that's going to be 273 Kelvin. 23 degrees Celsius is 296 Kelvin. So we just got to watch our units with the atmospheres here. Let's convert to atmospheres. So our units will all be consistent. 785 divided by 760, about 1.03. We plug everything in, 1.03 atmospheres. V1 is 3.84 milliliters. T1 is 296 Kelvin. P2 is 1 atmosphere. V2 we're solving for, and T2 is 273 Kelvin. So all of our units are going to cancel except for milliliters. So my V2 will be in milliliters. I'll have 1.03 times 3.84 divided by 296, and then times 273, 3.65. A diving bell is a container open at the bottom. As the bell descends, the water level inside changes so that the pressure inside equals the pressure outside. Initially, the volume of air is 8.58 cubic meters at 1.02 atmospheres and 20 degrees Celsius. What is the volume at 1.212 atmospheres and 20 degrees Celsius? We know that we have multiple pressures using this expression. What is the volume? So I'm going to solve for V2, so everything else should be given. P1 is 1.02 atmospheres. V1 is 8.58 cubic meters. T1 is 20 degrees Celsius, which is 293 Kelvin. P2 is 1.212 atmospheres. And T2 is still 293 Kelvin. So that's going to cancel. We don't need to worry about it. So my V2, my answer will be in cubic meters. 1.02 times 8.58 divided by 1.212, 7.22 cubic meters. You fill a balloon with helium gas to a volume of 2.68 liters at 23 degrees Celsius and 789 millimeters of mercury. Now you release the balloon. What would be the volume of helium if its pressure changed to 632 millimeters of mercury, but the temperature stayed unchanged? So again, we're changing pressure. We know it's going to be this type of problem. P1 is 789 millimeters of mercury. V1, 2.68 liters. T1, 273, 296 Kelvin. P2 is 632 millimeters of mercury. They want to know what the new volume is going to be. And T2 is the same, 296 kelvins. My V2 has to come out in liters. I don't need to worry about the 296s because they're going to cancel out. So 789 times 2.68 divided by 632, about 3.34 liters. So it looks like the majority of our work will be either using the ideal gas law or this expression. Just watch your units and be consistent with your units, and you'll be fine.